好，我也看一下宣传图。
把宣传片再放一下，徐敏啊。
好的，
网页啊之类都放一下。
好的。
OK。
好，我也看欣赏一下。
对，张老师，您再休息一下，然后那个还有3分钟，然后那个就是您准备一下。
好，
还有英文嘛？因为我们这个还像那个就是海外在直播。
哦，好，行，我还本来是准备了中文的，那我按英文讲也可以，没问题。
好的 ，OK，Thank you。谢谢啊。
Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment&Health. Eco-Environment&Health is a journal initiated by prestigious scientists with a strong editorial board, including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design, and broadcasting. The experts will accompany you like an harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. A 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a 3-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
Well, I think it's time to start. So first of all, I would like to take a few minutes to just introduce our journal. So Eco-Environment&Health is an international and multidisciplinary peer-reviewed journal designed for publications in the frontier of ecology, environment, and health, as well as the related disciplines. EEH focuses on the concept of One Health, green and sustainable development, dealing with interactions among ecology, environment, and health, and the underlying mechanisms and interventions. Our mission is to be one of the most important flagship journals in the field of environmental health. So currently we have like 4 scopes, sorry. So it's including ecology and biodiversity conservation, environmental behaviors, and bioprocesses of emerging contaminants, environmental human exposure and health effects, and evaluation, management and regulation of environmental risks. So please submit the paper to EH journal. And in the first 3 years, we waive the submission fee. So today we continue our talk at EH series. So today's speaker is Professor Hui Tring-Jung. Just I give some introduction about Professor Zhang. Actually, I know her, almost 20 years, right? When I was a graduate student in the US, and she is also a grad student. We started in a similar area, research area. Now, currently, Professor Zhang is a Frank Neff professor in the Department of Civil and Environmental Engineering at Case Western Reserve University. She got her Ph.D. from Georgia Tech. And she is also alumni of Nanjing University. She got her bachelor and master degree from Nanjing University. Her research focuses on the fate and transformation of environmental contaminants in natural and engineered aquatic environments, and the removal of organic contaminants from contaminated water. Her recent research areas also include predictive modeling for contaminant reactivity and sorption using both classical models and machine learning tools. Professor Zhang has published in numerous journals, such as Chemical Reviews, ES&T Water Research, and Applied Catalysis B. She has received six competitive research grants from U.S. National Science Foundations as PI. In addition, Dr. Zhang also directed research projects for many other federal and state agencies and industries. She is a topic editor for ACS ES&T Water and the associate editor for FESE. Hopefully, we also can invite you to be the editor of the EH. So today, she will give a talk in machine learning for the environmental research. That's welcome. So thank you, Professor Zhang.
Thank you very much, Professor Gu, for the invitation and for the introduction. Good morning, good evening, wherever you are. It's really my great pleasure to be giving this talk for EH. I believe this journal is going to be a very well-respected journal everyone wants to publish in. So today my talk will be really based on a framework of a ES&T feature article we published last year, but then I'm going to embed in a number of other papers we published in the last 3 years ago using machine learning to solve environmental problems. So I'm listing all of my co-authors through various projects, but because of the time, I will not go into their names. My talk will be divided into 4 parts. In the first part, we'll be giving a brief introduction to what machine learning is. And secondly, we'll overview what machine learning modeling have been used in environmental science and engineering field. And then my focus will be looking at how we build models using machine learning approaches. And finally, some challenges and opportunities. So firstly, what is machine learning? There's really no fixed definition for machine learning, but generally we believe that machine learning models use machine learning algorithms. These models are based on sample data or known as training data. The goal of these models are to make predictions or decisions without being told what to do. Because machine learning has very advanced algorithms, there are many advantages of building models like this. Firstly, they can easily identify trends or patterns, especially when we don't even know what the trends are or we have no idea what they are. And secondly, the performance of the predictive models usually is very good, especially if you have more data and be continuously improved. And finally, machine learning can handle multi-dimensional and multi-variety data, especially being appealing when we're handling complex environmental data. Because of these advantages, machine learning has been used in many fields you might be familiar with, such as consumer behavior prediction, self-driving cars, speech recognition. There's also been used to create animal-based food products using plants. Something learned recently is that the machine learning has been used widely in sports. For example, in racing cars, how do we optimize the different sports to make them more competitive? Very interesting applications. So because of these advantages, machine learning has also been gaining a lot of momentum in environmental field. In this figure, the y-axis is a number of papers published based on Web of Science. X-axis is between 1990 and 2020. So you can see over the last 20 years, we see this exponential increase in the number of papers using machine learning in the environmental field. If we were to break down into this pie chart, the red one is in water, so that means almost 50% of papers are using machine learning to solve water problems. The red is air, 27%. Dark blue is for soil, 21%, and is about 4% for sediments. So you can see there's many different fields have been really using machine learning already. This is really because the nature of the data we're looking at. So normally we divide the environment into 4 parts: water, air, soil, and sediments. And because of this rapid increase in the volume and complexity in environmental data, really we are limited by what we can do with the traditional statistical and other modeling approaches. That's really opening door for machine learning. So now what are the typical ways for machine learning to be used in the environmental field? Before I introduce that, I'd like to give you some background of what machine learning is. In case you are new to this field, you might be more familiar with something called multiple linear regression, or simply just simple linear regression, where we have a prediction target y, or this is a predictive dependent variable. And then we have a series of independent variables, x1, x2, etc. Once we use linear correlation to correlate y with this x, then we have a model, and that can be used to predict y if we're given many different x's. So this is a classical linear regression. If you think about that, with machine learning, especially supervised learning, is really much very similar. So for supervised learning, we have a lot of data as our input. This data can be in numbers, images, graphs, or text. This is really giving machine learning much more power to have different types of input data. And similarly, machine learning also has this output. This output can be either clustering. For example, we're clustering like a water body into type 1, type 2, type 3. Or it can be prediction or like regression. Like, for example, we predict the reactivity of contaminants in given treatment processes. So to link this input and output, then we have these algorithms in between. So this is similar to this linear regression for traditional multiple linear regression, except now we're using advanced linear or nonlinear algorithms, such as neural network you might hear of. This is exactly what we call as machine learning model, the whole thing, right? Once the model is being developed, then we can use it for multiple purposes. So far, there are 4 major applications. One is make predictions. Second one is detecting anomalies. Third one is identifying future importance. And the last one is discovering new materials and chemicals. Next, I'm going to give you a few examples of each of these applications. So firstly, making predictions. This is really the most important application for machine learning models. In fact, I think in general, we can say more than 90% of models are for prediction purposes. The first example is for PM 2.5 formation. So let's see if we want to know PM 2.5 concentration for a given city or given region. You might want to say, these concentrations depend on meteorological conditions, the traffic, the land use, etc. So those are considered as input. Then we can treat this PM 2.5 concentration as our output. By using algorithms, we can link these two and develop models to predict PM 2.5. This performance is much better than traditional multiple linear models. The second example is what we have been working on for the past 3 years or so, where we're trying to predict the reactivity of contaminants in different processes. I will say a little bit more later. But in this case, our inputs are either molecular fingerprints, molecular structures, or descriptors. The output is the reactivity or reaction rate constants. So in the typical way, we use linear regression, but in this case, we use machine learning algorithms. The developer models will allow us to predict the reactivity of these contaminants under different conditions. The second application is actually using models to identify the important features. The major way to do that is we quantify we basically assign a score to each input feature and find out which ones are important. So this is particularly important if we want to know if the model has learned the knowledge correctly, because machine learning models are usually considered as a gray box or black box, right? We want to open up the box and see if the model is meaningful. And this identifying feature importance will be one of the most important ways to do that. Again, using PM 2.5 as an example. So we know that the weather can impact PM 2.5, the pollution sources like power plants or traffic can impact PM 2.5. By building models and then look at future importance. If the identified features agree with what we know fundamentally, then we can have a better FESE in the model, right? We call that model interpretation. The next one, if we want to look at the soil uptake of different contaminants, we see how contaminants are moving up in different plants. Then we can also find out what are the most important properties. How about the soil properties? How about the contaminant properties? What about plants? All of them might be important, but some of them are more important than others, right? By doing this future importance, again, we can somehow determine if the model is really trustworthy. The third example is to detect anomaly. So this one is another extensive usage of models because the models are built on historical data. So in the historical data, mostly we have normal events, there's some abnormal events, but with the model, if we can predict abnormal events, then that's going to help us to locate that abnormal events and record that as anomaly. So example would be if you go to pipelines, there's probably some leakages or breakage at a certain location. And if the model can predict an abnormal flow, pressure, or water demand, very likely it's a burst or breakage of a certain location, and that's going to help us identify that either ahead of time or quickly afterwards. The second example, if you go to drinking water or wastewater treatment facilities, we definitely want to identify some failures in the treatment, right? We want to fix the sensors or fix a malfunctioning pipe or a pump or whatever devices we have. And this modeling can really help us identify those anomalies as well. The last application is to apply these models to discover new materials or chemicals. This is really, again, another extensive usages of these models because once the models are available, we kind of know what are the most important structures or properties that favor certain material applications, such as photocatalysis, such as certain sensors, or filtration or membrane, etc., etc. There are many different applications we can think of. The bottom line is, based on these models, we can identify the structure, the properties that are mostly beneficial to the target properties we're looking at. So now move on to the most important part of my talk today. So what is involved in developing machine learning models? I'm going to break this down into 3 parts. The first part is preparation for modeling. Second part is about the model development itself. And the last part is, once a model is available, what do we need to do to finish up the job? When we prepare for models, I feel the most important thing is we have to ask a correct question. Not all research questions should be solved with machine learning models. we have to be very careful, right? It's not like building model itself is not our goal. Like our goal is to use model as a tool to help us address certain questions. I'll give you an example of what we do. So what we do is trying to develop models for a large amount of chemicals. This is because there is over 850,000 chemicals being environmentally relevant. These have been registered at EPA's DSS Tox database. Some of the notable examples, some pesticides have been used annually over 2.5 million tons. For flame retardants, they have also been used over 2 million tons per year. In addition to this large amount of usages, we also have some serious consequences. For example, annual death associated with these chemicals can be about 1.6 million. Of course, there are many other potential risks. And what you can see is we have definitely a large number of chemicals that we should potentially be worrying about. And we particularly care about two aspects of these chemicals. One is that drinking water treatment and wastewater treatment are important to limit the risks of these chemicals, right? But in this treatment, we have many processes we have to care about, including advanced oxidation processes, absorption, biodegradation, membrane treatment, photocatalysis, redox reaction, etc., etc. The question we often ask is, how can we optimize the treatment so that we have a much better removal and a much more cost-effective way of removing them? The second question is, many of these chemicals, and once in the environment, we might undergo different transformations, such as absorption, biodegradation, redox transformation, photolysis, etc. A similar question we want to ask, so how fast can they transform, right? Are they persistent? Usually, the more persistent they are, the more of concern they are. So basically, these two applications require us to know the reactivity of chemicals in many different processes. So certainly with over 850,000 chemicals, it's impossible to work with them experimentally. That really means we need some modeling approach to help us. But traditionally, we often use something called quantitative structure activity relationships, or QSARs. This basically is one form of multiple linear regression where we have a predicted target Y that can be reactivity of contaminants. We have the X1, X2, X3, etc. These can be properties of chemicals. And this correlation will help us predict Y if we know chemical properties. Just give you an example of what we did last year. We developed a model to predict the reactivity of contaminants under reducing conditions. In this case, we first examined this traditional QSARS approach. And the y-axis is the predicted K value. We use this first order rate constant to describe the reactivity of contaminants. The x-axis is one of the descriptors we use. This is a normal energy or lowest unoccupied molecular orbital energy, because this normal energy describes how likely you will lose electron. So it relates very well to reduction of the chemicals. As you can see in this figure, each symbol here represents one group of chemicals. There's no need to know exactly what they are, but in general, I want you to bring you to attention to these different patterns, right? You see different symbols with different lines. The black line is one group of chemical, the blue line is a second group, red line is a third group, and this brownish line is a fourth group. So for each group, we have a very small number of chemicals involved. This exactly is the limitation of the traditional QSARs, right? We have to calculate this room energy, which is definitely not easy for everyone. And we have to only break two chemicals to very small groups. And so these relationships are very group specific, very narrowly defined. So we want to compare with the machine learning model we just developed, which also shows the y-axis as the predicted log K value, x-axis experimental log K value. Without going into details, the general pattern is all this chemical reactivity after prediction fall very well along this one-to-one line. So that means our prediction is quite accurate, especially considering there's only one model involving all the chemicals We also consider the experimental conditions, so it's definitely much more complex than those traditional QSARs. This is really showing the need for machine learning model in this particular case. So this is what I mean by formulating correctly what your research question is. You really have to demonstrate the need and the benefit of using machine learning models. And once you decide your question is definitely worth of exploring machine learning, then the next thing to do is, what kind of data do I have? Of course, I feel that the first step would be to say what kind of data are available in the literature. Usually, you will find out with a given environmental question, there's probably a very small number of data points being available, sometimes less than 100. You're lucky if you have over 1,000 data points. So when we collect this data, I want to warn everybody that that's where our expertise comes in. It's not like these computer scientists can replace us doing these models, because when we collect these data sets, we have to put our domain knowledge in and decide what representative data we should be using. Let me give you a simple example. So this patient complained to the doctor saying she has headache. And clearly, everybody can see what happened to her because there's an arrow going into her head. And any doctor or any average person can tell the reason. But if you just relying on a digital doctor who was trained by machine learning, well, we can input all possibilities for somebody to feel a headache, right? All the diseases we can think of. But very unlikely somebody would put in an arrow in the head as a reason to cause headache. But if the training data doesn't see this case, this digital doctor will never be able to identify the cause of the disease. That's what I meant. So when we develop these data sets, we really have to be very thorough in determining the most important features that are related to our predicting target. I will see this a little bit later. And we really have very extensive experience in the past 3 years to show this might be the most important thing to get a model done correctly. Once the data is finally ready, now we still have to pre-processing the data before we can continue to develop a model. This data pre-processing has multiple steps. We have to standardize, normalize, remove some duplicates or missing data. We have to remove some outliers, etc. Just give you one example. So for this data, we are having many different ways to represent them. I alluded to this a little bit earlier. The data doesn't have to be just numerical data. You can be creative to imagine them. It can be images, graphs, or even texts. So that, again, allows more flexibility to what kind of model we can build. In terms of outlier detection, so these might not be true outliers or true wrong data. So of course, they are wrong data in the literature, right? So we really have to screening have a certain criteria when we collect our data, either from the literature or through our own experiments. But sometimes some data points are just so different from all other data points. So they are just different. Doesn't mean they're not correct, right? If there are only few data points being very different, we still have to consider them as outliers because the model will not be able to learn them correctly. Another thing I want to mention is that a small trick we use is called a categorical parameter. So we just had a paper published probably a few months ago looking at modeling the reactivity of contaminants towards 4 different oxidants, such as HClO, ozone, and sulfur radicals. In addition to developing individual models, we want to have this one combined model so we can learn from each other. I will say a little bit more later. But in order to describe these oxidants in a model, you can certainly do computational calculations, right? But that's quite time consuming, and we also don't know the best descriptors that can describe these oxidants. So we simply used some categorical parameters. Just say we use 001 to represent HClO, 010 represents ozone, 101 to represent sulfur radicals. Just very simple one hot encoding. And the model can combine all of them in one piece. So the data is ready. And to build a model, we have to divide our model, the data set into training set, validation set, and test data sets. One more thing I want to emphasize is this data splitting is actually a very important step as well. So imagine if you have big data, 100,000 data points. Of course, a random split will be a natural way to do. But in reality, when we're facing environmental problems, my experience is we often have only a few hundred data points. Over 1,000, we call that very big data. But still, the data points are not big enough to be representative. So we cannot simply do random split. In my mind, this stratified sampling might be the best way. And this example is the paper we published, look at heavy metal absorption onto soil. In this case, we had 6 metals, but some metals have like over 1,000 data points, some have only a few hundred data points. So if we do random split, it's likely some heavy metals are more heavily represented in training, not much in test. So that's going to cause a lot of errors because test data set is going to be very different from a training data set. To avoid that kind of problem, we grouped all the same metals together, metal 1 in one group, metal 2 in one group, metal N in one group. From each group, we take 90% into training, 10% into test, so that we have maximum similarity between the training and test. For the training data, then we can continue to do cross-validation. This will be a reliable way to say the model can be robust. What is cross-validation? Let's see, we have this 90% of data. We can divide this into 9 groups. Each time we take one group, let's say group 9 as our test set, use group 1 to 8 to build a model. The second time we take group 8 as our test set, and the rest data sets also to build a model. And then we repeat this 9 times. And the average performance here will be the overall performance of the model. So you can see it's much more reliable than just take one set as the validation and train model like that way. So now we're moving on to the next step of the model development. When we develop models, I'm focusing on looking at regression models or supervised learning. We can do either regression modeling or classification modeling, right? Regression is simply you have continuous data, you want to predict for certain regression. For classification, you just simply divide the data into different groups or clusters. Either way, you have multiple metrics for evaluation purposes. What I want to say, there's certainly no best metrics. It's always better to choose at least 2 matrices for evaluation. For example, when we look at absorption of contaminants onto 4 different adsorbents, such as biochar, carbon nanotubes, GAC, and resin, we can develop 4 different models. The y-axis here is the predicted log KD value. The x-axis is the experimental log KD value. So in general, we do have a very good linear correlation as reflected by these Q-square values and these RMSE values. So we end up with 2 different matrices to describe the model performance. Once the matrices are developed, then we can select a good model. When select a good model, we certainly have to figure out what is the best algorithm to use, right? Because algorithm really determines the overall performance of a model. There are many different algorithms, but in general, we don't know which algorithm is going to be performing the best. Of course, if you have a large amount of data, neural network might be good performing, but for small data sets, we often encounter neural network actually is not the best one. We end up usually with different tree-based methods. In this case, we screened about 11 different algorithms, as I show on the bottom of this figure, and compare their root mean square error values. The smaller the root mean square error, then the better the performance. And eventually, considering the ability to handle missing data, how fast it can work, we end up using XGBoost. Next, we want to do some model evaluation. So once the algorithm has been selected, we certainly have to optimize the hyperparameters, we have to control overfitting, and obtain a model. Based on matrices, then we can evaluate whether the model is good or not, right? That's usually being tested by the test data set. But when we look at the model evaluation, the performance might not be very good as we hoped. So we might have to further enhance the model performance. There are definitely different ways we can do that. I'm going just to show two different approaches that we think are very, very good to use. The first one is called a transfer learning. Transfer learning essentially is we have a large model being previously available. And then we simply take the model parameters and apply it towards a smaller data set we have in mind. For example, there is a large data set used based on image set, develop something called a dense net that it can handle a lot of images, 100,000 images. So if we treat the chemicals as images, then we can start with this dense net and train this dense net with our specific data sets of chemicals. And this is what we call as transfer learning. Another idea is called data augmentation. This can really handle a small data set, also imbalance the data set, because we want to increase the diversity of data before we can train the models. One example is, again, looking at these images. So there are different images, but to increase the data set, we can flip the images, we can rotate. So essentially, one image can be rotated, flipped into hundreds of different images. And that's going to increase the data volume and allow us to determine these images without any bias. So let's look at the performance of these two approaches. So in here, the y-axis is a root mean square error. I said earlier, the smaller the value, the better the performance. And the x-axis is to look at training, validation, and test. So the red is with transfer learning, blue is without transfer learning. Usually, if the smaller the difference between these two data points, we say it's better because we want to minimize overfitting. So in this case, you can clearly see with the transfer learning, we have a much smaller difference in the test set, between test set and the training set. Data augmentation, this is another performance we compared. So the red again is with data augmentation, blue is without. And you can see for with data augmentation, the difference between the training and the test is smaller than without the data augmentation. That means for without data augmentation, we have serious overfitting. So data augmentation does help improve that. Well, once the model is ready, we certainly want to do a few more things to make sure they are really trustable, and then we can define their usage domains and be able to share the model with others. So how do we interpret the model? I think I noted earlier saying models are black box in nature, especially if you're relying on advanced neural networks. So we have to somehow open up the model so that they become meaningful to us. But just give you a couple of examples. When we use images when we use image to represent the chemicals, we want to make sure that the images can be read correctly. Like if we know here is a OH group, we know here's a keto group, we know this is the cyclic heterocyclic ring. We can look at the chlorine on the chemicals. So the images didn't know these are functional groups we care about. But if we want to identify these groups, it turns out these models can correctly find out the areas that correspond to these groups. So we definitely feel these images now have some chemical meanings to them. Another example is looking at the model interpretation. Yes, let's see, this is for reactivity of these chemicals towards hydroxyl radicals. So we have many different chemicals. Based on our chemical knowledge, in the center here is a saturated aliphatic chemical. We know for this chemical, the most reactive sites are the central carbons. And that's indeed what being found out by the model as highlighted by red. If we change the central chemical, add oxygen in the center, let the model to decide again, it turns out the model find out the correct sites as these carbon atoms again. If we replace oxygen with sulfur, the model is also very smart in find out the sulfur as the most reactive site. If they further replaces sulfur with this keto group, it turns out, interestingly, the model can also identify this keto carbon to be the most reactive sites. So through these different interpretation approaches, we know now that the model has learned these sites correctly, and we have more faith in such a model. Once the model is believable, we are able to decide, how widely can this model be applied. Of course, non-models are universally applicable. Let's look at the chemical space as an example. Early on, I said the chemical space might be 850,000 chemicals. The center here might be just our small data sets or the number of chemicals our data set can cover. How can we determine whether a new chemical is within our domain or not? And we're using something called a similarity calculation, right? We can calculate how similar this new chemical is in terms of a chemical structure or chemical properties to these chemicals in this shaded area. If they're similar enough, we say they are within our domain and the model can handle them. But we have to watch out, depending on what method we use to represent the chemicals, we might end up with different chemicals being treated as within the domain. So on the bottom, there are two different methods, A and B. A is based on molecular image and a convolutional neural network. B is based on molecular fingerprints. So you can see, use two different approaches, we actually identified different chemicals to be outside of the domain. The majority of the chemicals are still similar. There's some minor differences in what the chemicals to be outside. Finally, the model is ready to be deployed. So of course, there are many different ways to apply these models, right? We definitely want users to be really creative to apply our model, but I want to encourage everybody to be also creative, to think about how we can apply our models, right? So we can give ideas to other people to say where this model can be applied. And this is one example where we worked with Professor Wang from Zhang University, my good friend over there, where we developed a model where to look at the global soil absorption of heavy metals. Once the model is available, they downloaded these soil properties from global soil data sets and apply the model to the soil. Now we can look at this absorption capacity based on the soil properties globally for 6 different metals: cadmium, chromium, copper, lead, nickel, and zinc. You see, this is really nice. With this model, if you go to anywhere in the world, we can tell you what the absorption capacity of the soil is towards a certain heavy metal. And that has many different applications. If you want to grow crops there, if you want to move industry there, or you want to do soil remediation. So finally, I want to move on to challenges and opportunities. Of course, I mentioned a lot of how powerful this machine learning can be, but we're still facing many challenges. And one major thing I think is the data scarcity. Although we're looking at big data, right, there's tons of data available. For any given research question, usually we are really running short of data sets because there's no general rule of what data to be used and how data are generated. And they're probably just being very biased towards very small number of conditions, very small number of chemicals, or very small number of operating conditions. Just give you one example. So here, when we want to develop models for different oxidants, you can think about there's tons of studies on advanced oxidation processes, but when we spend a lot of time trying to go through the literature, we actually found that only somewhere between 143 and 342 compounds having valuable data for those chemicals. Very small data sets to start with. Even worse, this data is not balanced. Let's look at hydroxyl radical as an example. So the x-axis here is number of is experimental log K value. The y-axis is the number of chemicals having reported log K value. You can see a lot of data points are centered at like pH log K between 9 and 10. Beyond this range, we have very small numbers. So this data set is very imbalanced, and that kind of model will not be very robust. So what we did in this paper, we decided to combine these models either into one data set or combine 2 or 3 data sets together so that they can learn from each other. And if you want to compare the performance, you see in here, the y-axis again is a root mean square error. The red is for single model for each oxidant by itself, and the green is for unified model. So in general, we do have improved performance for the last 3 oxidants. Of course, for sulfide radicals, the performance is slightly worse. And the reason is that if you look at the bottom here, for sulfide radicals, the log K values are much, much higher than the other 3 oxidants. So these different data set ranges might be a major reason for the performance not being very well. The second challenge is often overfitting. Overfitting means we have very good performance on the training data set, but a very poor performance on new samples. Sometimes even detecting overfitting is a challenge, but a common way to overcome this is to do a cross-validation. Of course, to have a balanced, diverse data will be another important consideration. Other concerns, we do want to have as many features or the most important features to be considered, right? If you have an important feature not considered, no matter how many data we have, very likely the model is not going to work well. Other concerns, don't overtrust the machine learning models. These are just another tool we're using. They're not necessarily better than statistical tools, and we probably want to have a more balanced, right, comparison of different approaches if possible. And of course, not all problems can be solved by machine learning. And what we want to promote is a good way is to balance or to integrate machine learning with the traditional approaches, because we want to add our mechanism understanding into the models. One example is we published a paper, even now it's over a year and a half ago, where we want to develop absorption models for mixtures of contaminants. This y-axis is one group of chemicals, the x-axis another group of chemicals. Each square here represents the root mean square error for this model prediction. So this is based on traditional model. You can see the red represents large errors, blue represents small errors. When we combine this theoretical model with this machine learning model, we end up with much better performance, and also can be widely applied. So this opens up a new door, right? We're not just separating these two as conflicting ideas, but rather we kind of look at them being synergistic or being working together. We want to share our data, right? We want to share our model so that our community as a whole will be developed in a much better way. And when we collect data, we want to make sure our data quality is high, they are coming across the forces, and we probably want to design more experiments, design more models to increase the data sets. And during this, the quality control will be very important. We want to be creative in applying our models, especially now we'll have over 107 million chemicals as an example. How can we create new knowledge? How can we make new models that can handle such an enormous amount of chemicals will be a new direction. And finally, I know everybody is eager to take on these new tools, but learning some fundamentals will be very important. I'm just listing a few papers we published in the past few years. So on the left-hand side, there's all oxidation. The first 3 papers are on hydroxyl radicals. The bottom one is on 4 other oxidants I showed earlier. On the right-hand side, the upper one is on reduction. The bottom three are somewhat on absorption, either as a single solute or bisolute, or how we describe organic chemicals. And then the last one is this predicting this heavy metal absorption onto soil. So with that, thank you very much. I think my time's out, and I'd be happy to answer any questions if you have.
Thank you, Huichun. It's a wonderful presentation, and I think it's a pioneer studies in the machine learning environmental studies. So it's a very great talk. Thank you very much. So,
Thank you.
Sure. So now, if any people have questions, just raise your hand. So I will let you ask a question. Otherwise, you can just write on the board. So we also can, ask Professor Zhang to answer your question too. Let's see. Yeah, so now we have some questions from the, the board. So one question is that, so the first question is to the two questions, right? So the first one is how to deal with categorical variables in machine learning model. For example, if we have a population data set, we could either train two models for the men and women, or we can also use categorical variable gender as the input of the model and train a single model. Which would you like to choose and why?
Okay, yeah, very, very interesting question. Do you want me to answer this first, or you want to go through both questions first?
I think can be probably the first one.
Okay, yeah. I think you can do it either way and decide which one is giving you better results. Because when you look at a categorical variable, man or woman, assign 0, 1 or 1, 0 to either one. That's an easy one to do. There are many different ways to assign categorical parameters. The one I'm showing is a simple one, but I think one of my students was screening 6 different approaches. Those are downloadable packages we can use from GitHub, very easy to use. But I don't think any particular one is preferred. It's really, other than this man and woman, as do they have other things to share in common? Do you need a model for men by themselves or women by themselves? Again, based on the research question. I feel blending them together would be preferred because you have a larger data set and then you might have some similarity between those two type of groups. So your data might be more diverse that way.
All right, thank you. So the second question is that regarding the application domain of the machine learning model. So as we know, the application domain of the model largely relies on the completeness and the representativeness of the training data. However, in the case of making prediction for a future time point, how should we guarantee that this model is suitable for future scenario, especially for long-term prediction, as there may be a structural change. Also, sometimes we make prediction for future. We may also use the future predictions for the input variables. How should we deal with the issue of propagation of the errors? So that's the second question. It's a long question.
Yeah, that's a long question, but I think it boils down to one thing, right? How can we reliably determine the applicability domain of a machine learning model? This is certainly a big challenge we're facing. It's really coming back to the original data set. For the applicability domain, rather it's like how diverse is your own data. The domain cannot be outside of your the original data set. So I'm using the chemical as one example because that's something I'm most familiar with. But I can give you another example for water quality later on. For chemical structures, we try to find out how many representative chemicals we have based on similarity calculation. Let's say we have a large data set of 850,000. This probably will be the entire chemical space we're going to compare to. But for a small data set we have, whether it's hydroxyl radical or it's adsorption, we might have only 1,000 to, let's say, 5,000 chemicals. So we calculate similarity between these two and find out how many chemicals in this large chemical space can be covered or have similarity that's high enough that we have a reliable prediction for, right? This is one scenario. But I think that the question you're looking at here is more like time series data, right? Because you're looking at a future scenario. So for now, we have a paper in review that is to predict algal bloom in Lake Erie based on time series data as well. So let's say we have different water quality, we have weather condition, we have probably bloom occurrence, and we want to forecast, let's say, in the next 10 days, whether are we going to have bloom or not. But that applicability domain is much harder to define, but we can reserve some of our time series data as our training set, some as our test set, and that's going to define our domain. How reliable we are, I mean, that's always a dynamic question. We can never be true to 100% true. So how reliable we are is the performance on the test set. That's going to give us an indication of how reliable our prediction will be for the future. So hopefully that answers your question.
Oh, thank you. So another two questions. I think he's from my group. So somebody is joking that we are hyperparameter tuning workers, but we know that this is also biased in terms of modeling. So could you please share with us some of your experience or recommendations while tuning the hyperparameters?
Yeah, that's very interesting. Well, of course, we're not hyperparameter tuning workers. And if you think yourself is just simply tuning hyperparameters, you're probably just on the beginning phase of doing machine learning models. Of course, I don't really tune hyperparameters by myself. But to me, if we are doing high quality scientific research, the most important thing we're doing is to solve questions. Tuning hyperparameter is a small portion of solving that question. So before we develop models, as I said earlier, you have to identify a very meaningful research question to start with. And then the second most important thing is what kind of data do we have? Do we have enough data? Do we have enough feature descriptors to use as the input? Once those are determined, then you can tune hyperparameters. But tuning hyperparameters, to me, is just computer work, right? You select a different hyperparameters, you let the computer doing the work. So my experience, to be honest, I don't do this modeling by myself. I always just ask my students to do that. I really don't know what kind of recommendation you're looking at. You mean how to tune them so they are better, or how to tune them so they are more efficient? I don't know if there's a good way. I know my students have been using Bayesian optimization. Sometimes they use a grid search to help them. I think these are two major things they're using now. And certainly the transfer learning is very helpful because you have existing model you can borrow, and then you can fine tune based on the existing model. So that's going to save you a lot of time. And usually the performance is much better.
All right, thank you. So also another question that, could you please share your opinion on the progress of the environmental related literature, text mining? Can the current state of the art reveal or even predict the trends of the environment topics and issues? Thank you.
Yeah, okay, that's a very interesting topic. I don't know if there's a lot of research on this text mining. I know Jason Ren from Princeton published a paper last year that they were trying to mine text and find the trends in the environmental research. Other than that, I'm not aware of many other researchers that have been doing that. For us, we're mainly mining literature for data, not for text. I was discussing with my students whether it's worth of writing code to mine the text to collect data, and somehow they feel that's probably taking even longer time, because for each specific research question, you need a lot of domain knowledge to screen the literature and then probably to find out what data we can use. Using this text-based mining might not be sufficient for us to get all the literature we wanted. So I kind of remain a little bit skeptical of what this can achieve. I might be biased because we're not being successful yet in doing that. So we're still mainly relying on manual kind of mining, like we collect all the papers and then collect all the data. And we have to set our criteria to say what is good data, what is not good data when we combine them into our model. A very interesting topic that we should look into that a little bit more in the future.
Mm-hmm. Okay, thank you. So somebody want to ask question from the audience, please. The CY Wu, please. You can just ask. Mm-hmm. No? So, all right. So another question is, maybe we have two more questions. I think the time is running out. So Professor, thank you for your sharing. If I use model interpretation and found that there are some problems with what the model has learned. For example, it overestimates some variables. Then how can I modify the model? Thank you.
Yeah, very relevant question. So if you think the model hasn't learned correctly, I would firstly check the original training data set. Couple of things you can check. Firstly, do you think you have enough data? Very likely, if you have a small data set, the model is not going to learn correctly. And secondly, do you have the most important input features being considered? The most important features, meaning the features that are most likely to influence your final predicting target. If you are not including some of the most important features, only these non-relevant or not most important features being included, and very likely the model is not going to learn correctly. If both of those have been cleared, you might want to look at probably different algorithms, right? Some algorithms will probably perform better than others. What we tend to do is do some optimization and find out the best algorithm. Sometimes even ensemble models will work. So there are many different things you can try, yeah.
Okay, thank you. So how can I guarantee the accuracy of the prediction result in a machine learning study? I think you mentioned that.
How do you guarantee? So that's certainly a big question, right? That to guarantee the prediction result, you just have to follow the steps. It's many steps I mentioned today throughout my talk. And then if you want to know more details, the paper we published last year lists a lot of detailed steps in my recent paper. So in nutshell, you need to have a high quality input data. You want to have a trustworthy model development process. You want to have a proper evaluation of the model performance. And then you want to interpret the model to make sure it has learned the science correctly. Only after those steps, then you can say, you're more comfortable about the prediction accuracy of the results. It's definitely not one thing that can guarantee that, right? Everything I said so far should probably be kind of be of interest.
So maybe last question.
Sure.
Sorry, last question.
No problem.
Okay. So when we collect the data from the papers, maybe sometimes the variation of parameters are different. Just like collecting the data of soil adsorption for each kind of soil, the pH of the soil is only one value, but the other parameters obtained by the experiment of the soil may have many values. So if we input this data to train, is that reliable?
I would think very likely. So I would do that initially. You set multiple columns, right? Each column would be for one property. Let's say you have one column for pH, the second column for soil, let's say organic carbon content, another column for cation exchange capacity, just some 3 examples. So with the 3 columns, you might have the pH be the same for all these rows, which is fine. But you have different values for organic carbon and cation exchange capacity. So this will be the initial set. Of course, you will have many other columns. Each one will be a separate property. In this case, because pH is the same, it probably doesn't make a difference whether you use this pH column or not. But other columns you will have to include because very likely it's going to impact soil absorption. Yeah, I do think that is reliable.
All right. Thank you. Thank you, Professor Zhang. Like for, like a very, lots of informative like talk. So due to time, I think we stop here. So thanks again. And since EH at Talk is a series of webinar, so we will have our next presentation on next Monday at 9 p.m. So we invite a researcher from Pakistan, actually. He's also the editor of the EH journal.
Okay.
So if you are interested, so please you can pay attention to our social medias. So WeChat and Twitters, and also we have website. Min, can you show the website?
Okay.
Show the website.
Let's wait a moment.
Yeah. So if you're interested, you can always check our website, also our social medias for more information. So we have this series. We try to keep it twice a week, so you can get more information about these webinars. So this is from previous the talks. Yeah, this is for the journal -eh.com. So that's our website. So if you need any information, if you want to get any information, including our editorial board and also the how to submit your paper, so please look at our website. So maybe we can start from here. Thanks again, Professor Zhang, for your wonderful presentation. Hopefully, you can contribute to our journal and maybe in the future give another talk. Thank you very much.
Yes. Yes, thank you. Thank you for having me. And if anybody who has questions not answered, please feel free to reach out. I will be happy to email you back with my answers.
All right.
Okay.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Okay. Bye.
Okay. All right. Thank you, everyone. Thank you for your attention. Okay. See you. See you next week, next Monday. Bye-bye.
Yeah, my email, if you Google my email, you should be able to find it.
All right.